While we're waiting for the microphone to get fixed, I'd like to introduce Peter Raymond, who's going to be talking to us about inland water and dissolved fluxes, and hopefully carbon as well.
Yeah, mostly carbon. So I'm going to talk about inland water, dissolved fluxes, and I thought we'd start by kind of walking through how our thinking of these systems have evolved, and how the evolution of our measurements and our thinking of how they evolved have made it into sort of these global diagrams. This is the diagram that I cut my teeth with, and rivers were indeed included. And the way they're included, right, is they are this connection between terrestrial and oceanic systems. They're a passive connection. What they do is they take a little excess organic matter from the difference between organic matter production and destruction on land. It's modeled that there's a little extra production on land, and they deliver that to the ocean. And then they take some carbon chemical weathering. Some of that originates from the atmosphere, some of that from minerals itself. And they also deliver that to the ocean. And then once in the ocean, what happens is this organic matter is converted back to CO2, and this inorganic carbon that was delivered mostly as bicarbonate is also turned back to CO2. And it fuels this pre-anthropogenic source of CO2 from the oceans to the atmosphere and sort of closes, if you will, the pre-anthropogenic loop. Okay, and right around this time, maybe to use a corny dad joke, there was a watershed event in my field. That's a better response I get from my kids than with my corny dad joke. Where there was a large amount of outgassing seeded the Amazon. Some of that from streams, rivers, and lakes, some of that from wetlands, on the order of half a gigaton. And really from this point forward, there was a new term that came in, this sort of river outgassing term. Again, a pre-anthropogenic flux. But whenever, of course, you add something to the global carbon budget, something has to make room for it. And the way it's made room for is this sort of difference between organic matter production on land and organic matter oxidation on land becomes greater, right? Where before it was 0.4, now it's 1.5, mostly due to this riverine outgassing term. And then there's been some other papers since then. Here is an evasion term that's slightly higher. A flux that I'm not going to talk a lot about, except to come back to at the end, is there's also now this idea that there's a lot of burial of carbon within inland waters. So carbon that leaves land, never makes it to the ocean, gets buried within inland waters itself. And this burial term, in fact, also could be quite large. And this paper is put at 0.6 gigatons. And then here is an effort that I was involved in, led by Anthony. And if you sort of squint your eyes, you can see the Excel spreadsheet, right, that we use to come up with these global fluxes. Not quite back of the envelope, but it's not far from back of the envelope, where we did sort of a zonal attribution of inland water CO2 fluxes, looking at small streams, larger rivers, lakes, and reservoirs in these different regions. Right, and indeed came up with this number of around 1.2 gigatons. But for quite a while, this was sort of the state of the state with respect to the evasion rates. And if you look at the last IPCC, this is sort of where we stand, right? We still have this riverine flux that really hasn't changed much in size that goes to the ocean. However, we have this freshwater outgassing term, and now this burial term is also included in the global carbon budget, all as these pre-anthropogenic fluxes. And so John Cole sort of put this together very simply but eloquently, right, where perhaps before the way we were thinking about inland waters was this passive pipe, and we're moving to thinking about them as much more active pipes, right? Where if there is a large amount of sediment storage and a large amount of CO2 evasion, one ramification of this is that a much larger amount of carbon must be leaving land to sort of subsidize those fluxes. And in fact, of all these fluxes, this is still the one that we know best, and I'll come back to this towards the end of the talk. And we're really working through these two fluxes, and this one is done by difference currently. And I'm going to spend a bunch of time talking about this one, partially because it's one of the ones that's most dynamic right now, and by dynamic, I mean it's moving around a lot, and we're really working hard to try to nail this down. And it's something I've worked on recently. And so, just like in the oceans, if you want to figure out how much CO2 is coming out of your inland waters, you need to constrain three parameters. You need to know how much CO2 is in the water, you need to know the surface area of your inland waters, and you need to know something about the physics that drives the exchange across the air-water interface. What are we doing for CO2? Right now, our community is working with a database of alkalinity and pH. We're well aware, and we're getting more aware, that this is not a great place to be in. In fact, the calculation of CO2 from alkalinity and pH in inland waters is not as straightforward as it is in the ocean. And so it's not an ideal situation. However, there is a database of direct measurements of CO2 in the globe. Another bummer is that when you start working this data, there isn't really a strong correlation of these CO2 numbers with anything, which is not great for your scaling. But the concentrations can be quite high, right? Where the global average in my analysis was 3,500 microatmospheres, so about 10 times the atmosphere. And you can put together these regional maps, and we did this simply by interpolating. And you can see that there are some sort of regions with high levels of CO2, particularly and potentially in the tropics. And if you look at the spatial distribution of our alkalinity and pH measurements, they're perhaps arguably even less ideal than the oceanic figures that we've seen. There's a ton of measurements in the US and in Europe, some good density in South America. Other than that, we're not really doing that well, and in particular, we think these are the regions of hotspots, and we really have no measurements in them, which is not ideal. One of the more surprising things when I started to do this 5 or 6 years ago is there actually were very few estimates of the surface area of water on land. You would think, due to the importance of water as a resource on land, that this is something that would have been worked out fairly well. In fact, there was no, particularly for streams and rivers, there was no spatially resolved map of the surface area of streams and rivers for the globe. So this is something that our community has been starting to figure out, and basically have to come up with methodology to produce these spatially resolved estimates, and I'm just going to show you some of the data sets we use. This is a watershed, right? It's a watershed in Tennessee, about 20 kilometers wide, 40 kilometers north to south. And on this are a few of the data sets that are available to us. The global data set is in red, right? This is a hydroshed data set, which gives you spatial representation of really rivers, right? As you can see, it misses all the small streams, the headwater streams. And so this is the data set that we have to work with globally. This blue set of lines is from the National Hydraulic Data Set for the US. This is sort of kind of the gold standard right now. And what we do now, or what I did, is you sort of looked for relationships and tried to figure out how much the global data set was missing based on the United States data set, and then tried to project this sort of across the globe using scaling laws. And so when we did our global scaling, we basically added a stream order to the global data set, knowing that NHD Plus appears to miss one or maybe even two stream orders itself, because this map does not have the ephemeral, or misses a large amount of the ephemeral streams that come and go as the water table goes up and down. So, and this is the data set we use for length. So you're gathering up the length of streams across the globe using this NHD plus data set, and you're trying to add in some stream orders using scaling laws that I'm not going to get into, based on relationships that you're making from regions in the world that aren't representative but have a higher resolution data set. And then what you have to do is you have to try to somehow assign a width to each and every one of those lengths. And the way we do this right now is we've been sort of scouring the literature and trying to create these hydraulic relationships between discharge and width. So this is from thousands of systems in the United States. This is basically gauging stations in the United States, and this is sort of a metadata analysis, not from gauging stations, where you're trying to establish the relationship between discharge and width, and then using global maps that we have for discharge to then assign a width across the entire globe. This relationship is well known, and as you can see, it's fairly good. So there is a relationship where width is equal to discharge raised to an exponent times a coefficient. But you can see even with these two data sets, we have different exponents and different coefficients. And when you scale them out across the entire globe, these are the differences you get in the surface area of streams and rivers using those two relationships of width that the community is now using. Right? You get two differences. One is the total surface area of streams and rivers. Using one, you get 760,000 kilometers squared. Using another, you get around 500,000 kilometers squared, which is a considerable difference. But you can also see that the proportion of that surface area that's with very small streams versus large rivers is also different depending upon which one of those relationships you use. And so we know there are biases in both of these relationships. We have an idea of what the biases are. So kind of what we do right now is just average the two and try to move forward. And it's also a very interesting area for science, just trying to understand what controls regional variation in these types of relationships. Anyway, one reassuring thing that you do is when you do this over the globe, there is a relationship between the surface area of streams and rivers and the amount of rainfall in that region, which is intuitive, right? Wetter regions have a greater surface area of streams and rivers. And this is actually, these types of relationships are also quite helpful in your scaling. And so this is what the surface area map looks like. Right now we're estimating that about 0.5% of the land surface is covered in, this is just streams and rivers. And these were some of the other back-of-the-envelope calculations that existed before. So perhaps arguably in the upper end, the community is also trying to figure out how much of this is blocked by ice and how much of this dries up on a regular basis. But again, sort of high surface area in the wetter regions of the world, which is intuitive. And then the last one is gas transfer velocity. And we know in the oceans, right, the gas transfer velocity is controlled by wind over the surface. In streams and rivers, this really isn't the case. Turbulence is generated by water flowing over the bottom, or perhaps water, the sinuosity of rivers creating shear on the sides. And so we had to do this metadata analysis basically to look for controls of the gas transfer velocity. And it scales in watersheds with the velocity of water and the slope of your watershed. This makes sense from first principles, which I don't have time to get into. You can currently gather up slope of all those stream length segments for the globe using available data sets. And so then what you have to do is assign a velocity of water to every single stream segment in the globe. Luckily, very similar to width, there's hydraulic equations that link velocity to discharge. Basically, discharge at a site is equal to width times velocity times depth. And so that's why these relationships exist. So we use those same relationships, and then we assign a K sort of an average K to every single stream segment in the globe. And so now what we're doing is just putting those three together and summing them up. And this is what you get for streams and rivers. This is the first sort of spatial map of the gas evasion from streams and rivers. And one of the punchlines was the number, when we do this, is 1.8 gigatons, so significantly higher than some of the previous estimates. With 70% of it coming from 20% of the Earth's surface, and these hot spots being the tropics, right? They have high surface area, they have high CO2, and they have, in general, higher velocities of water. And so this is one of the latest estimates. And just a quick digression, one of the ways that you can get to 1.8, there are basically three main sources of CO2 in inland waters. And one of these is soil CO2, right? And you can do some back-of-the-envelope estimations and get to a fairly large amount of soil CO2 coming out of soils and evading probably in your small streams. And in general, we see the highest fluxes in our small streams. The other source is terrestrial organic matter that leaves land but then is decomposed in transit to the ocean. And for this to become important, you basically have to start to assume that about twice as much organic matter leaves land as makes it to the ocean, and it's respired en route. And this probably occurs more in your larger rivers, and is probably to some degree fueling the CO2 evasion here. But you're still kind of far away. And one of the really important ones, and this has been demonstrated somewhat in regional studies, is that wetland and riparian zones really can pump quite a bit of CO2 into inland waters. And this is probably a fairly significant component of the total. And if you assume that a large percent of wetland NPP is transferred to inland waters and abated, right, you can easily start to approach this. I have it as 2.2 here because lakes and reservoirs add another 0.4 gigatons. So the total inland water evasion is in fact 2.2. So that's how you get there. So what else has been going on? There has been another paper that's come out recently that is modeled it just from the hydroshed spatial extent and up. And they've published an estimate of 0.6 gigatons for the globe. And comparing that to the estimate I just went over, if you want to compare oranges to oranges, it would be about half as large. Okay? So there's a paper out there quite recently that's saying that this estimate is twice too large. However, even more recently, a paper out of Alberto Borges' group where they've had some significant campaigns in the sub-Saharan Africa, and this is sort of direct measurements of CO2 and K, they get an estimate of 0.4 for this region alone, where we had it at 0.1. So 4 times larger than us, and a significant fraction of this 0.6, not leaving much space for the rest of the inland waters to evade CO2. So this is kind of where we're at, right? We have a big number out there right now. One paper saying it's kind of maybe way too high. One paper saying probably could be even way too low. And the community is sort of working hard to try to improve our methods. And so I just wanted to spend a few minutes to talk about the other two dissolved fluxes, organic carbon and inorganic carbon in the form of bicarbonate. For Dennis and Craig's recent book, we wrote the riverine chapter, Rob Spencer and I spent a little time going over all the historic estimates of DOC flux to the ocean. And there isn't a huge amount of spread in them. However, when you start reading the papers, you do find that they're quite incestuous in the data that they use. And our modeling approaches are not really that sophisticated. And so although they're sort of honing in on a number of about 0.25, there's still actually a lot of room to improvement, and there could be some surprises, I feel, that could come out of this field. One interesting thing to think about is that if we know that they're tightly correlated to discharge, and the annual global discharge seems to vary by about 25%, so these fluxes at least vary globally by the same amount. And this is a figure that Rob put together where he tried to collect as much data he could from some of the large rivers in the world, which is one of the ways we sort of came up with this number here. And you can see that if you do this, you have about 36% of the land draining into the ocean and about 50% of the global ocean discharge. With DIC and alkalinity fluxes, we're in pretty strong shape. And this is because we know that, and we've demonstrated that there's strong relationships in a region between the amount of alkalinity or bicarbonate coming off the landscape and the climate of that region and the lithology. And we have actually now fairly solid global lithology maps. And so, you know, we have good maps and we have a good sort of mechanistic understanding of what controls this flux. And so this number of about 0.35 petagrams as bicarbonate is probably not going to move around unless there's some sort of drastic response to climate change. And we also sort of know that the hotspots are in these sort of regions of Southeast Asia and some of northern South America. So not only do we have an idea of the amount, we have a pretty good understanding of the spatially where this is coming from. And so if we return back to John's active pipe, right, and we put two numbers that are out there in the literature, one thing that we're starting to feel is that there's probably 3 or 4 times more carbon leaving land that's making it to the ocean. And our community is quite interested in understanding the dynamics and what controls that cycling and where it's happening. There are large uncertainties on all 3 of these, maybe slightly less on this one here. One interesting thing is one of the better sort of regional papers just came out this year for the United States. And if you put their numbers on it, the ratios here are pretty similar to the ratios here. So the United States appears to be acting like the globe with respect to the ratios of these different fluxes, although there's no reason to feel like you could scale these up to the total amounts. And then, I think this crowd understands this, but one of the more important things is our community is really far behind in attributing what the anthropogenic component of this fluxes are. There are lots of sort of process-based detailed studies that have demonstrated anthropogenic components to all these fluxes. However, there is not a firm understanding globally of what the anthropogenic component of these fluxes are. There is this one paper by Pierre that I was involved with, right, where he tried to put together an anthropogenic component to these fluxes. And the important thing to remember is that if there is an anthropogenic component to these fluxes, right, the only way to make room for it is to change the residual terrestrial sink. I would say our communities are really far away from being able to firmly assign what this anthropogenic signal is, but it's something we're very interested in and trying to get more and more active with. Okay, I'll stop there.
We have time for a couple of questions.
I'll just tell more corny dad jokes if
Yeah.
you guys don't ask questions.
I noticed you had Antarctica in white on all of your maps, but Greenland was colored in. Wondered what the story was there.
Yeah. Well, actually, that global map of streams and rivers that actually ends at 60° north. So we're guessing at Greenland and most of the Arctic. We're trying to get relationships that we get below 60° north and apply them to the Arctic. And so those are probably one of our areas of the largest unknown. Antarctic, I'm not aware of any even sort of regional guesstimate on the surface area of these systems, so they're not included.
Hi, Hi, Pete. 50% of global discharge is DOC. Do you have any idea, or are there estimates for how much of that is labile or refractory?
No, there's really not a good understanding. I'd say if I had to give that talk, the message to this community, it's probably a lot more labile than is thought. The stuff that makes it out seems to be highly photoreactive and is protected from photodegradation during transport. So that's a process that is a very strong potential link between the two communities in particular.
Yeah, Jim Bishop of Berkeley. The question is the particulate organic matter fluxes and carbonates. Have people estimated those for the
So
global
particulate carbonates?
Yeah, particulate carbonates and particulate organic matter.
Yeah, there's a lot of interest in particular organic carbon. It's not something I work on. The community has a fairly good handle on it, and there are a few people who have models for it. The trick, of course, is trying to figure out the anthropogenic component of that, because we know that we trap a lot behind dams that weren't there previously. So we have a decent estimate on what that number is. Trying to figure out what that number was is perhaps the really interesting component of that research. And there are also estimates of PIC fluxes. It's not something that's very actively studied that much, but if you go back to even Maybeck's original papers, he has PIC in there. I want to say they're like 0.1 gigatons, something like that.
So given how hard it is to get PCO2 accurately from alkalinity and pH, and given the quality of some of these pH measurements in fresh water, what's the status of getting more direct PCO2 or better constraints on that critical issue with respect to the global fluxes?
Right.
People working on that?
Yeah, so a few years ago, my feeling was we were going to try to get the community together and figure out how to use the pH and alkalinity results better, but it's so hard because some of the data comes from groups where they didn't have a firm understanding of how hard the pH measurement actually is, and it's probably plus or minus 0.5 units, which is horrible. And so now the community would love to be able to get together and start to collate direct measurements of CO2, but also try to enable some of those areas of the globe that don't have those direct measurements to be able to make them. And so that's what I'm currently interested in trying to do. But we're probably still at least 5 years away before we have any type of database